Welcome to Developing Graphics Frameworks with Python and OpenGL, Part 30, Geometry Polygons. In the previous video, you learned how to render some basic shapes using this new graphics framework. We've talked about geometry classes and material classes. We'll put them together to create a mesh object. And in fact, in the last video, we created this example. This is test 29. And if we build and run this example, we'll see a spinning cube. That's a great shape. It's one of the most basic three-dimensional shapes, but we'd like to expand the number of shapes we can render in this framework. So over the course of the next 4 videos, we're going to go back to the geometry classes and add some more shapes. So in this video, in a little bit, we'll talk about a Polygon class, which you can then use to create triangles or pentagons or hexagons or any two-dimensional shape you want. And then in the following videos, we'll talk about how to use formulas to generate surfaces in three-dimensional space. So for example, spheres or cylinders, cones, and pyramids. But first, we're going to return to our code base here. And before we get started, there's a few things we should do to make our lives a little bit easier and a little bit more convenient. The first thing I'd like us to do is to take this class. This is test 29. And there's a lot of code in this class that we're going to repeat in every single example. Right? We're going to have a whole set of imports. We're always going to need to import these 5 classes. We'll always need a geometry and a surface. We'll always have an initialize function. We'll always set up these objects and add a mesh to the scene. And so there's lots of things we'd like to do. So let's go ahead and create a new file in our main directory. I'd like us to save this right away, and let's call it test template. This will save a lot of time going forward. Testtemplate.py. And just to make our lives easier, let's go to test 29. Let's select all that code. So Control A to select all and Control C to copy. Then let's paste it into test template. And let's keep everything except some of the code we might not need as much. So for example, we'll always have these import statements. We might add different import statements for different geometries or materials, but for now we'll keep these. See, we'll always need a renderer, a scene, and a camera. And I'll leave this mesh and adding the mesh to the scene. Maybe I'll take this statement about the camera and I'll move it up closer to where the camera's set up. I'm going to delete the code about the backdrop since we don't always need that. And let's also delete the code for rotating an object because we might not always want to rotate something. And that's it. That's the code that we'll use for our template. Really, it's just the bare bones of what you need for the initialize and the update functions. And so once we've got that class, let's go ahead and save that. Next thing I'd like to do, again before diving into the geometry class, since we're going to be creating a lot of geometry objects, let's go over to the geometry class. So in the geometry folder, right, we've made a rectangle geometry and a box geometry. And in each of these classes, notice that we set up attributes, and we have to kind of keep typing in the same code. Right, we declare an attribute object, we import the attribute class, declare an attribute object, and then add it to this attributes dictionary. Whenever there's code that you seem to be repeating again and again, it's always good to write a function to perform that for you. So in the geometry class, I'd like us to create a new function. And this new function, let's call it add attribute. Now there's 3 pieces of information you need for an attribute. You need the name of the data type, the name of the variable, call that variable name, and the actual data itself. And so let's define this new function. And really, this is a one-liner. So self.attributes, that's the name of our dictionary. And we're adding something new to this. So in brackets, we'll put the variable name. That's our convention for adding things to this dictionary. And this is going to equal a new attribute object, which has a certain data type in the actual data. And so this function is going to be used a lot to simplify a lot of our code. Of course, since we're using attributes now, we should also import that. So up at the top of the geometry class, let's go ahead and say from core.attribute import the capital A attribute, the class. All right, and to see how this is going to make our code a little bit simpler, let's see how we would modify, for instance, the box geometry class with this. And since we have a new way to add attributes, we actually don't need to import the attribute class. So I could delete that. And then down at the bottom of this code, where we did this, I think it reads a little bit nicer to say the following. Self.addAttribute, it's our new function. It's a vec3 associated to the shader variable vertex position. The actual data is in the array position data. In fact, this almost looks like a traditional variable declaration, right? A type, variable name, and a value. And we'll do the same thing for this next line of code. We're going to add an attribute. Again, it's a vec3 associated to the variable named vertex color. And it takes in that array of color data. Right, so that should fix everything. Let's go ahead and save this. And just to make sure there's no typos, let's go back to test 29 and give that a run. So let's go ahead and build that, and hopefully we'll see the exact same spinning cube from before. There we go. So those changes were a-okay. And hopefully they'll make the things we're about to do a little bit easier. So now onto the main topic, we're going to go ahead and create a geometry class. So going back to the slideshow, right now we're interested in, well, we're going to start off with circles, which they're related, right? They're flat, like polygons are flat. But the reason we're really interested in this is we're going to use a formula to automatically generate the points we need for each polygon. And so, just as a refresher, polygons, technically regular polygons, they're two-dimensional shapes, and we want all the sides of the polygon to have the same length, right? And all these angles within the polygon have equal measure. And that's what makes it a regular polygon. And eventually, we'll have to divide this into triangles. So we'll also note that of each of these triangles, these angles will also have the same measure. All right, to create the formula for the vertices of the polygon, we're actually going to use the equation of a circle and choose a certain number of equally spaced points around that circle. Now, to come up with a parametric equation of a circle, we're actually going to use trigonometric functions, sine and cosine. In particular, for a circle of radius r, the equations for a circle are x equals r times cosine t, and y equals r times sine t. So x and y are both functions of the parameter, or the independent variable t. And t will range from 0 to 2 pi, so that's what it takes to go through a full cycle of the sine and cosine functions. Now, when you think of the equation of a circle, you might be more used to the implicit equation, right? The equation in terms of x and y and no parameter would be x squared plus y squared equals the radius squared. That's just a different way of representing the same shape. In fact, you can see that these equations, these parametric equations in terms of t, satisfy this slightly more familiar equation just by substituting them in. If you plug in r times cosine t in for x, then r times sine t, plug that in for y, and then if you expand that out, there's a trigonometric identity you would need to use to simplify this. Sine squared plus cosine squared equals 1. Right? It'll actually reduce to this equation. You'll get a true result out of that. Right, so this is the parametric equation of a circle. And the important step is to figure out, well, what values are we going to plug in for t to generate these points? And the idea is that these points, you can think of them as lying at a certain angle from the x-axis. So for instance, to get from this point, to get from the x-axis to what I'll call the first vertex on this polygon, I have to go through an angle of some measure a. To get to the next point, again from the x-axis, right, I need to rotate by an angle of 2a. To get to the third point from the x-axis, I have to rotate by an angle of 3a. And what's this base angle a? Well, it depends on how many sides your polygon has. Right, in this case, I have a nonagon, a 9-sided polygon. So the angle here, see, an entire revolution would be 360 degrees, or 2 pi radians. Right, and so I'm dividing up 2 pi radians into 9 equal parts. So that would be 2 pi divided by 9. Or if you prefer degrees, 360 degrees divided by 9. But most computer science functions require radians. So this angle here for this example would be 2 pi divided by 9. So to generate these different points, we'll set up some kind of a loop and iterate through that loop and generate these points, and that will be our position data. Now the other thing we'd like to do to make these really kind of visually interesting is to associate vertex colors as well. Right, so what we'll do is we'll assign different colors to each one of these vertices, but kind of in the same pattern, so each triangle looks the same. So in other words, here, for each one of these triangles, we'll use white for the center point, red for one vertex, and blue for another vertex. And so you can really see the triangles, so they pop out at you. So here on the left, I've got a triangle. Here in the middle, there's an octagon. And here on the right side is something interesting. If you glanced at this quickly, you'd probably say that's a circle. But if you looked really closely, it actually has 32 sides. It's impossible, because of the discrete nature of computer graphics, to draw a perfect circle, but we can approximate it with a many-sided polygon. And so that's what we're going to do when we start writing code. All right, that being said, that's the plan. Right, we have the formulas that we're going to use to generate some points. And we can actually test this out right away since we created the template rendering example. So let's go ahead and return to our development environment. And let's make a new class. You might recall, to keep the code organized, we're going to keep all of these examples of different shapes in the geometry class. So go ahead and right-click the geometry folder and let's make a new file. I'll close some of these other ones. This new file, we'll call it Polygon Geometry. So let's save that. Polygon geometry.py is the name. Let's see, what do we need to do here? Well, we're extending the geometry class, so from geometry.geometry, import geometry, and make sure that that G does not auto-capitalize to lowercase. It should be capital. And then, since we're doing some trigonometry, we need some things from the math package. So from math, I want to import the sine function, the cosine function, and pi, the constant. And now, let's make our class. This is class Polygon Geometry. Extends the geometry class. In the initialization function, there's a couple of parameters we could use to specify what our polygon looks like. First, we should give it some number of sides. And secondly, we could also give it a radius. Now, we don't necessarily always think of polygons as having a radius, but it's really just the distance from the center to a vertex. And it makes sense in the context that we're generating the points from the equation of a circle, which we always think of as having a radius. So the constructor will have two parameters. We'll give them some default values. So maybe size is equal to 3 and radius is equal to 1. So first I'll call the super initialization. And next, most importantly, I need that base angle inside the polygon. And that's 2 times pi, that's a full rotation, divided by however many sides we have. All right, let's make some lists to store the position data and the color data. And now let's make a for loop. All right, so for n in the range of however many sides we have. We're just going to start appending things to each one of these arrays. So position data, first we'll append the center. Right? These are always going to be centered at the origin. Next, position data, append. Now we need to generate those vertices according to the formula. Right, so again, the formula is going to be whatever our radius is times cosine of some multiple of our angle. Radius times the sine of that multiple of the angle. And the last vertex is just going to be 0. Our polygons are going to lie in the plane where z equals 0. So they're kind of facing the camera by default. All right. Then we need to do the same thing again, except we want the next vertex as we go around the polygon. So instead of n times a, let's make that, in parentheses, n plus 1 times a in both those functions. All right. If you want, of course, we can line these up. Not very easily, though. All right, so those are positions for each triangle. Of course, we want vertex colors. We'd like these to look nice. So next, let's do color data. And you can really use any 3 colors you want. I like to put white in the center, so it kind of looks like it's glowing a bit. And then I'll do a red color, RGB 100, and finally a blue color, RGB value 001. All right, and there we go. We've populated our data arrays. Now we can use that nice new function to add attributes to our geometry. And we have to make sure this is lined up with a for. So self.add attribute. First we're going to add a vec3 corresponding to the variable vertex position and give that position data. Then we'll add a second attribute, also a vec3. Oops. This one called vertex color. That takes color data. And once we're done, we need to count the vertices. All right, so the draw arrays function knows how many we need. And that's really it. Let's go ahead and let's make a sample application, which is going to go ahead and render some polygons for us. All right, so once we've got that code, let's go ahead and in our main directory make a new file. We'll call this test30.py. Oh, it's not where I typed that. Let's save. Let's call this test30.py. And again, to make our lives easier, we have this template file we made. You can hit Control-A to select all, Control-C to copy, our new test, Control-V to paste. Okay, we need to import our new geometry. So from geometry.Polygon Geometry, import Polygon Geometry. Now, all we really need to do is change the geometry that we have set up. So here, instead of box geometry, don't blink or you'll miss it, Polygon Geometry. I do want to use vertex colors. That's all we need to do. Let's go ahead and save this and build. And if everything went okay, we should see a triangle by default. Hey, we've got a triangle. Let's try changing this. Let's see if we can do an octagon. Let's see if we can generate those three shapes. So let's say I want sides equal to 8. Save and build. There's our octagon. Let's make something which looks circly. Let's do 64 sides. How does that look? It's even more sides than the picture I showed you a moment ago. That's pretty cool. Can we do 128? We can. What will it look like is the question. Very nice. All right. So we can make polygons. Excellent. Now, if you really wanted to, if you're feeling ambitious, you could actually create extensions of the Polygon class for specific common shapes. So for example, let's go back to geometry. Let's right-click and let's make a new file. Let's say from geometry.polygon geometry. Let's import Polygon Geometry. And let's say, for example, we want to, well, let's make this generate a hexagon for us. It's not syntax highlighting yet because I still need to save this file, so I should do that now. Let's save this and let's call it hexagon geometry.py. There we go. Now, if we want to make this class polygon, not polygon, let's call this hexagon geometry. Right, it's going to extend the Polygon Geometry class. So we'll define the initialization function. It's going to call the super function initialization, and we could say sides equals 6, and that would generate a hexagon automatically. One more thing we should add, just so we don't lose some of the functionality of the Polygon Geometry class, we should add in some kind of a radius. Now, admittedly, this does look a little funny to say radius equals radius. Here on the left, it's the named parameter of the super constructor. And this radius right here refers to the value that was passed in for this parameter. And so you could put in whatever radius you want. That will get passed along to the Polygon Geometry constructor. But again, since we're developing a graphics framework, we want to keep the end user in mind. So it's nice to sometimes create classes like this to simplify the development process. So here we have hexagon geometry. Let's go back to our test and let's test that out too. So from geometry.hexagon geometry, let's import hexagon geometry. And again, in order to change our demonstration, all we really need to do is change the name of the geometry that we're rendering, save and build. So hopefully we'll see a hexagon on the screen. Fantastic, there you go. So now you can create infinitely many more shapes. It's a very efficient time. All right, and that'll really wrap it up for two-dimensional shapes. In the next video, we're going to start talking about a way to create functions, kind of like this polygon functions that we used, but a little bit different. Using functions to generate some interesting three-dimensional shapes. That'll be in the next video. Thanks for watching.